Let me start by thanking the organizers for the kind invitation to speak here. It's my first time in Brazil, and it's a pleasure to be here. So I want to talk about this recent paper with my collaborator Alex Schenkel, where we proposed a way of constructing 3D integrable field theories from 5D Chern-Simons theory, or some higher gauge theory variant of Chern-Simons theory. And I know this is not quite about string theory, but there's some flavor of gauge theory and integrability for sure. So what I want to convince you today is that this is a very natural higher dimensional generalization of the well-studied now proposal of Costello, Whitney, and Yamazaki for describing 2D integrability from 4D Chern-Simons theory. So the main motivation for studying these higher gauge theories is that they provide a very natural gauge theoretic origin for the lax formalism. Or lax integrability. And I want to convince you that in this three-dimensional setting, this will come naturally from looking at this 5D 2 Chern-Simons theory, which I'll introduce shortly. So let me start by going 2 dimensions down and thinking about 0 plus 1 dimensional integrable systems, so finite dimensional integrable systems with just a time. So I claim that the relevant theory to look at here is 3-dimensional BF theory, or it's called 3-dimensional mixed BF theory, which you can think of as a level 0 limit of normal 3D Chern-Simons theory. And the claim is that this theory knows everything about Hitchin's systems, Hitchin's integrable system. Okay, so the action is the following. So it depends on 2 fields, 2 one-forms. There's some normalization, and then the action is just BF. So it's an action on a 3-dimensional space, which will be taken to be R, the time direction, cross CP1, which will become the spectral plane, and the action is B times the curvature of A. So B here is just a field with a dz component. So on CP1 I have coordinate zz bar, and here I have coordinate t. So B is just bz dz, and A is a one form with just a t component and a dz bar component. So I said this is a level 0 limit of Chern-Simons. If you start from Chern-Simons with level k, and you scale the AZ component by 1 over k, and you take the limit k to 0, you label the rescaled field AZ as BZ, and this is what you get. Okay? So this is just some scaling limit of 3D Chern-Simons. So why is this relevant for describing Hitchin systems, or in general finite dimensional integrable systems? So first of all, we should say this is a gauge theory where B transforms by conjugation and the connection A transforms like a connection. And so the key point is that the equations of motion, or let's say the direct way to see that this has something to do with integrability, is that if you look at the equations of motion and you work in the gauge where AZ bar is equal to 0, then the equations of motion are just that the remaining components BZ is holomorphic, and also the component AT is holomorphic. And crucially, the time evolution of BZ is just a commutator with minus AT. Okay. So what these equations tell you is that BZ and AT are holomorphic, and this last equation is very familiar. It's the lax equation for a finite dimensional integrable system. Okay, so there's a caveat here is that because I'm working on CP1 for this example, to say that something is holomorphic on CP1 is to say it's constant, so there's no spectral parameter dependence, so this is quite sort of a spectral parameter independent lax equation. But you can actually tweak this formalism by adding some line defects. So if I look at BF theory plus line defects, then what I get is that instead of this 0, I'll get that this is equal to a sum of delta functions, same as this one, and this will tell me that BZ and AT are both meromorphic with poles at the location of the defects in CP1. So these are defects along R and then located at specific points on CP1. So I get a meromorphic lax pair, BZ and AT, which satisfy this lax equation on shell. Okay, so this is the sort of simplest example, the toy model, where you can see why these Chern-Simons theory have anything to say about integrable systems. The next example, which is something we've already heard about from Rodrigo Pitombo, is that 4D Chern-Simons theory knows everything about 1 plus 1 dimensional integrable field theories. Okay, so again, to get an interesting integrable field theory out of it, you should really put surface defects. So the action here will be, we've seen this already in the talk by Rodrigo. So it's an action for a single connection A, some normalization, and then you integrate over R2, or in general some two-manifold cross CP1. And the action is some one-form, meromorphic one-form omega wedged with the Chern-Simons 3-form. So omega is some meromorphic one-form. And A is a connection which only needs a dt, dx, and dz bar component, because the dz component drops out from wedging with omega, which is some meromorphic function times dz. Okay, and this is the usual Chern-Simons 3-form. So okay, so again, this is not quite gauge invariant. You need to impose some boundary conditions, in this case, on the gauge field A to make this theory gauge invariant. So we have gauge invariance. So this will happen again in 5D. So the point is gauge invariance requires imposing some boundary conditions. On A at the poles of omega. Okay. But once you know it's a gauge theory, you can again move to the special gauge where AZ bar equal to 0. You'll be left with a connection with two components, dt and dx. And the claim is that in that gauge, AZ bar is equal to 0. The equations of motion tell you that the remaining components of A are meromorphic. So you get omega wedge d bar of A is equal to 0. And secondly, that the curvature along R2 of A is 0. Okay, so the first equation is telling you that A is meromorphic with poles at the zeros of omega. That's what this equation is saying. And then once you know that, this is just basically a zero curvature equation for a field theory. Okay, so it's meromorphically dependent connection A, which is flat. And it's flat on shell because these are the equations of motion of that theory. So this is the zero curvature equation. Okay. Let me just draw the picture here. So the point is that these surface defects, this will come up again later in the 5D story, so it's useful to have the picture in the 2D case. So I'm working on R2 here, and the defects are located at specific points on CP1, because that's where the one form omega has poles, and they're located along the R2. So they're surface defects at specific points in CP1 along R2. Okay, so now another important thing so this is all story by Costello Yamazaki. And there was an important preceding work with Witten, so which I need to talk about for motivation. So also, yep. Yeah. So, oh, sorry. So this, so here omega is a generic meromorphic one form, but when omega has no zeros, so for technical reasons, then you can look at 4D Chern-Simons theory plus certain line defects in the R2. And the work of Costello, Whitty, and Yamazaki is that this is telling you about, so let me say this is Costello, Whitty, and Yamazaki. And they show that this is related to lattice integrable models. Or, in other words, quantum Yang-Baxter equation. So let me just give you a very brief summary of how this works. So now we're still on R2 cross CP1. But we're only looking at line defects. So we have certain lines in R2 located at specific points in CP1. So there's first line, let's say gamma 1 at some point Z1, and then another line, gamma 2 at some point Z2. So what they looked at was expectation values of Wilson lines along these two lines, tensor product of Wilson lines along these two lines, in some representation V1 and V2, say. And what they showed is that the expectation value of a tensor product of Wilson lines along these two curves, so along gamma 1 and along gamma 2, this is actually just an R matrix, which depends on the location of the defects in CP1. So R1, 2, so R Z1, Z2, which is a map from V1 tensor V2 to itself. And so the reason why this guy satisfies Yang-Baxter is because if you take 3 lines at along different directions in the R2, let me draw it. So this is in R2. If I take 3 lines, because the theory is topological in the R2 direction, then I have the Yang-Baxter move, where I can move this this particular line across the point where the intersection of the other two is, and then I get the Yang-Baxter equation. So this expectation value of Wilson lines automatically satisfies the Yang-Baxter equation. So this is sort of a way of encoding solutions of the Yang-Baxter equation within this 4D Chern-Simons theory by looking at line defects in the R2. Yeah, so these are straight lines, yes. Otherwise, there's something called framing anomaly. So, but this is just a setup which, yeah, I want to recall, not in detail, but because I'll look at something similar in the 5D story. Okay. Okay, so so now the question is, if we move 1 dimension up and look at 2 + 1 dimensions, well, the first obvious question is, what is the lax formalism that we're aiming to reproduce, and what will be the appropriate gauge theory for doing so? Okay, so in 2 + 1D, yeah. So the first question is, what is the appropriate lax formalism? And how do we get it from a gauge theory? So what will be the 5D gauge theory? So it's 5D because you can see from the previous examples that we're always adding 2 dimensions, which will be the spectral plane, but ultimately we're working with a field theory on the other factor. So if we want to work in 3+1, or in 3 dimensions, we need a 5D gauge theory. So what will be the 5D gauge theory? So there is obviously lots of possible ways of constructing lax formalisms in high dimensions. So the most well-known one is the anti-self-dual Yang-Mills in 6 dimensions. So the point is that there's a reduction of this to 3 dimensions, which is called the Bogomolny Yang-Mills-Higgs in 3 dimensions. So this is the equation. It's the Hodge star of f of a is equal to dA of phi, the Higgs field. So the point is that this is a 1D reduction of anti-self-dual Yang-Mills, which is known to be a sort of mother theory for 4D integrable field theories. So this is one proposal, a lax formalism that encodes the... so there's a lax formalism for this equation, and that would be then a lax formalism for describing 3D integrable field theories. And then there's some work of Bittleston and Skinner, which appeared shortly after the original proposal of Costello-Yamazaki, where they describe 4D integrable field theories from 6D holomorphic Chern-Simons, and as a special case, they reduce to 3D and describe this kind of equation. So this can be described, they showed, from 5D, what's called partially holomorphic Chern-Simons theory. And it's on what's called mini twistor space, which as a manifold is just R3 cross CP1. So again, the idea is that this CP1 will become the spectral plane, and the R3 is where the field theory lives. Okay. So this is not what I'll be talking about. This is a proposal for describing 3D integrable field theories. But the formalism I want to discuss is a very different type of 5D Chern-Simons theory. So the motivation is the following. So in 2+1D, yeah. So the motivation for this work was that in 2+1D, we would naively expect the lax connection of a 3D theory to have a two-form component. And I'll give 2 motivations for this. So let me call it B. So actually this dates back to some papers from the 90s where people speculated about high dimensional integrability, and these ideas already emerged back then. So there's a paper by Alvarez Ferreira and Sanchez Guillen, also some earlier work of Jean-Michel Maillet, where they speculated that you should have such two-form component because, for example, you can use it to integrate along surface, Cauchy surfaces, which are 2-dimensional, to obtain integrals of motion. So naturally, integrals of motion should be built by integrating something over a 2D surface, the Cauchy surface, and therefore you should have some two-form in the game to produce higher dimensional integrals of motion. So the first motivation for having a two-form component. No, they will not be Lorentz invariant. Yep. So for a long time, people tried to build Lorentz invariant 3-dimensional integral field theories and always failed. In this language, it's fairly clear why they failed. You cannot do it. Not that I can't see any way to do it. So okay, let me first give the other motivation. So we would like, well, we expect these integrals of motion to be built from surface integrals. So expect integrals of motion in a 3D integrable field theory to be given by surface integrals over Cauchy surfaces. So the picture is now we're working in 3D, and a constant time slice is a surface now. So let me draw a constant time slice. Let me call this gamma t. So this time direction is vertical. And so what we would expect is some sort of surface integral or area ordered integral of some two-form field along this Cauchy surface. So this would be some sort of higher monodromy or two monodromy. And there's a nice poster at this conference by Enrique, where these kind of surface integrals appear. So I think there's some relation between what I'm talking about and what's on that poster. And so this is one clear motivation for integrable field theories in 3 dimensions. You want to have this two-form to be able to construct these integrals of motion. Another motivation comes from looking at what would happen if we try to generalize this story to 3 dimensions. So the other motivation is we would like that this 5D Chern-Simons theory, if I add now surface defects in 3 dimensions. So remember here, I was looking at a 2-dimensional field theory, or 2-dimensional space, but I looked at only line defects in it. Now that I'm working in 3 dimensions, I want to look at surface defects in that 3-dimensional theory. And this should produce, somehow, Zamolodchikov tetrahedron equation, which is known to be a 3-dimensional generalization of the Yang-Baxter equation. So the picture is, again, we're in 3 dimensions. I want to put my 5D theory on this 3-dimensional volume. So let me say it's R3 cross a CP1, which will be the spectral plane. And I want to look at surfaces in this 3-dimensional space. So let's say this is surface 1. It's at a point Z1. Then there's another surface 2, which intersects it at a line. So this will be surface 2 at a point Z2. And then I would have another surface intersecting those at a point, or intersecting that common line at a point, which is at a point Z3. And the point is, because we now have surfaces, we would like to look at Wilson surface operators, and namely the expectation value of 3 such Wilson surface operators. So in different representations, let me say this is surface integral of B along gamma 1, and similarly up to V3 gamma 3 B. And this should give me an R matrix, which now depends on 3 coordinates, R, Z1, Z2, Z3, which goes from a tensor product of these 3 representations to itself. And again, because the theory is topological in the R3, by design, this, if you take 4 surfaces, they will intersect in, so let me draw the tetrahedron equation. So you'd have 3, so these are the 3 lines obtained by intersecting 3 of the planes. And then the 4th plane would be like this. So I have my 4th plane here, and the common intersection point of the other 3. And then I can move that plane across to the other side of the triple intersection. And this would be equal to, so the tetrahedron is flipped upside down. I get something like this, where the point is now here, and the plane that I moved across is on this side. So this is the Zamolodchikov's tetrahedron equation. and it's sort of it would be automatically satisfied by having a 5D theory which is topological in the R3 direction. Okay. But the point is that we would need a two-form field to be able to construct these Wilson surface operators that we could then take expectation values of to get this tetrahedron solution. Okay. So hopefully this is enough evidence that we want a two-form field. And so then the question is, well, what's the right language to have a two-form field as part of a connection? And the point is, or the answer is, we need to look at higher gauge theory, which has a one-form and two-form field as part of its connection. So the idea is to consider a higher gauge theory. Version of 4D Chern-Simons, and the field content would be what's called a two connection, which has two components, a one-form A field and a two-form B field. And this would be a theory on X. The total manifold which will be, let's say, R3 cross CP1. So this should be the setup. Okay. So now I can define the 5D analog of 4D Chern-Simons theory. So for that I need a few ingredients. So it's a higher gauge theory, so it's going to be built on a notion of higher gauge group. So let me now talk about this 5D 2 Chern-Simons. So it's 2 Chern-Simons because it's for a two connection. So what we need is what's called we need to fix a Lie-2 group, or more precisely what's called a strict Lie-2 group. But this is a very simple object. It's just a pair of groups G and H, and then two maps, one going from H to G, a group homomorphism from H to G, and then some action of the group G on H. And they should satisfy some very simple requirement, namely we have an action also of G on itself and an action of H on itself, and the map T should intertwine all these actions. That's the only requirement. So this is a notion of Lie-2 group, and there's a corresponding notion of associated Lie-2 algebra, which is just obtained by differentiating this data. So we get Lie algebra G and H, and then some map from Lie algebra homomorphism from H to G, and some Lie algebra action of G on H. Okay. There's also, for technical reasons, other maps you can define, so you can differentiate this map in different ways, and there's another useful map which will be an action of the group G on H itself, on the Lie algebra H. So I call it the same way because they're distinguished by what you feed to them, but this map will also be relevant. I have 10 minutes. 12. Sorry? 12 minutes, okay. So I told you that this will be a theory for two connections, so I need to tell you how two connections transform and also what they are. So a two connection will be a one form valued in G and a two form valued in H. So this is why there are two different groups. So what is a two connection? A two connection, which will be the field content of my 5D theory, is a pair AB, which is consisting of a one form on the total space valued in G, and also a two form on the total space, but now valued in H. Okay. And what is a gauge transformation? So it should act on this pair of objects, and it's going to consist of two objects. So a gauge transformation now will consist of a pair So it will consist of a group element G and also a one-form gamma. So G is some what you would expect a gauge transformation to be for a one-form field valued in G. So it's a group-valued function. But then I also need a Lie algebra-valued one-form to transform the B field. Okay. So this acts on the pair AB as follows. So just to write some concrete expressions. So it transforms almost like a normal connection. But then there's also an offset by the one-form gamma. So T star takes something valued in H and spits out something valued in G. So I can then subtract it from this one-form field, which is valued in G. And similarly, B prime transforms in this non-trivial way. So you have the group valued element G acting on it, because this is H valued, and then the group valued element acts on it. Then you subtract the curvature of gamma, which is valued in H, a two-form valued in H. And then you have the pair, there's this alpha, which takes two Lie algebra things, one in G and one in H. Okay, so that's the gauge transformations. So in a high gauge theory, there will also be two gauge transformations, which would sort of be transformations between gauge transformations. But for technical reasons, these are not well defined unless the curvature, the connections I'm looking at are fake flat. So this is a very sort of subtle point which bothered us for a long time. The point is that we want the action to be non-trivial, and if the connections are fake flat, then the action completely degenerates. The action I'm going to write down. So we just had to ignore these two gauge transformations. And the point is that in the resulting theory, we see some remnant of these theories, but of these gauge transformations. But the point is that these still remain to be properly understood from a mathematical point of view, so we just ignored them for the time being. So I'm almost in a position to write the 5D Chern-Simons action. So remember, the 4D Chern-Simons action is the Chern-Simons 3 form wedged with a meromorphic 1 form omega. The 5D theory will be defined in a similar way, but to get something 5-dimensional, which I want to integrate over X, which is 5-dimensional, if I wedge with the 1 form omega, I need a 4 form. And so the point is, for a 2 connection, there's a natural Chern-Simons 4 form. So if I fix a pairing between G and H with certain properties, I can define the 2 Chern-Simons 4 form, which is as follows. So it's Chern-Simons of a 2 connection, and it's defined as, or the expression is given as the curvature of A, which is a 2 form, minus another 2 form, and that's paired with a 2 form. So this is a 4 form, and minus some extra term, which is an exact derivative. So you might be wondering, why does this have anything to do with Chern-Simons theory? It turns out that this is precisely a Chern-Simons term. Namely, I can write it as, so if I introduce a curly A, which is A plus B, and this is living in some generalized notion of Lie algebra with some grading, so it's called a DG Lie algebra, then I can write down the normal Chern-Simons action. So it's A paired with a half DL of A. So there's the notion of derivative on this differential graded Lie algebra, plus 1 over 3 factorial, the commutator, or the Lie bracket in this Lie algebra, and then there's a pairing on this Lie algebra. And this, if you work it out, it's exactly the expression here. So this is really an honest-to-goodness Chern-Simons thing, Chern-Simons form, but it now just depends on two components, the A and the B field. So finally, I can define for you the Chern-Simons 3 form, Chern-Simons in 5D. So I define 5D 2 Chern-Simons action in the same way as 4D Chern-Simons action was defined. So I take my 4 form and I wedge it with omega, which is some meromorphic 1 form. So now this is on R3 cross CP1, which I called X all this time. So I take omega wedge, the Chern-Simons full form. Okay. 5 minutes? Yeah. So from this point onwards, if you're familiar with the 4D story, it's almost identical. You just have to work a bit harder because there's more fields, but the procedure is really the same. So this is not quite a gauge invariant theory. You need to impose some boundary conditions on A and B to make it gauge invariant. The violation of the gauge invariance is at the poles of omega. So there are, again, some surface defects located at the poles of omega. So I have my R3 cross CP1. And my now volume defects are at the poles of omega. So these are some marked points, Z1 up to Zn. And they lie entirely in the volume R3. So the volume defects located at specific points on CP1. So maybe let me skip the procedure of how you extract a 3D integrable field theory from this. If you're not familiar with it, this will be too quick. I don't have time to explain it. But it really is exactly the same procedure as in the 4D story. I'll just tell you the steps. So basically, you have to to construct a 3D theory from this. So constructing a 3D integrable field theory is done in the following way. So first, as I showed you in the two examples in 1 and 2 dimensions, you have to work in a special gauge where the z bar components are all 0. So you work in AZ bar is equal to 0 again. And now we also have to work in the gauge where BZ bar I, so I is any of the other components from 1 to 3. These should both be 0 in that gauge. So when you do that, the bulk action reduces to the integral of omega wedge d bar A B. And so the bulk equations of motion for A and B just tell you that A and B are respectively holomorphic, or rather meromorphic with poles at the zeros of omega. So the second step is to impose the bulk equations. And what that does is it sets A and B to depend meromorphically. On the CP1 with poles at the zeros of omega. And then finally, this is a step I can't explain in detail. You have to solve the boundary equations of motion, the boundary conditions, sorry, which what it does for you is it expresses the fields A and B in terms of some field content which will be living on the surface defects. So there are going to be edge modes living on the volume defects. The edge modes are there to sort of ensure gauge invariance of the whole theory. And what solving the boundary conditions does for you is it expresses the lax pair in terms of these edge modes. So there are 2 edge modes. There's a group valued field and a Lie algebra valued one form. And then same for B. It depends on both of these fields. Okay. So these are just edge modes living on the surface defect. So they're really 3D fields, and they are the field content of your 3D theory. So the point is, once you've done all this, you really end up with a 3D theory for the edge modes. So you get an action S that depends only on the edge modes. And it's a 3D action living on R3. And its equations of motion are, by design, the flatness of this 2 connection, which is the following. So there'll be the flatness of A. Or A is not quite flat, but it's flat up to B. So there'll be T star B. So this is called fake flatness condition. And then, so M, sorry, is R3. It's the 3 manifold. And then dB plus B commutated with A is 0. So these are the 2 conditions expressing the flatness, the full flatness of the 2 connection. And these, because of the original steps here, they depend meromorphically on the spectral parameter. So this is sort of the 3-dimensional well, the proposed three-dimensional lax formalism for these three-dimensional integrable field theories, which was speculated a long time ago in the 90s, but this is sort of a recipe for constructing these theories, like applying this machinery and just churning out lots of theories with these lax connections, depending meromorphically on the spectral parameter. So as far as I know, there were no known examples of this, but we have a first simple example of the Ward equation, which is a three-dimensional version of the PCM with a Lorentz breaking term. Because the PCM itself is not integrable, if you add a Lorentz breaking term, it becomes integrable. And we get all the right conditions that Ward imposed on these on this Lorentz breaking vector. Has to be of length 1, and the metric has to be 2, 1. And all this comes out from choosing a specific one-form omega with the right number of poles. And this equation drops out. We get some generalization of the Ward equation, but essentially the Ward equation is contained within it. Okay, so I'll stop here. Thanks very much.
Thanks, Benoit, for the talk. So we can move to questions.
So I heard that the solution of a tetrahedral equation is not known for general Lie algebra, but do you think using this Lie2 algebra you can find a solution to this tetrahedron?
Yeah, I mean, there are some recent papers I've seen that, one by Talalev, where he describes that underlying these tetrahedron equations are Lie2 algebras, which is consistent with what we're saying. So I don't know how many solutions are known of the tetrahedron equation. I know I've seen papers by Bajanov and others where they built out solutions, but this would again be sort of a systematic way of building solutions of the tetrahedron equation. If you could quantize this 5D theory when omega has no zeros and apply a similar procedure to what Costello-Witt and Yamazaki did to this 5D theory, just computing Wilson surface OPs.
So you said that you needed to have straight lines because of some framing anomaly, and now do you need to have straight planes? And how would you look at the theory that you said, this principal kernel model plus something, and understand what are the particles and where are these straight planes coming from?
So there are two stories also in the Costello-Witt and Yamazaki and Costello-Yamazaki. So Costello-Yamazaki is about building field theories. Costello-Witt and Yamazaki is about lattice models. Here as well, there are two stories. So the theory where you have volume defects in the entire of R3 located at points on Z, on CP1, this is like the Costello-Yamazaki story for field theories. And here you're just building actions for classical integrable field theories, and you build them by just choosing a one-form omega and applying this procedure I told you about. The story of Costello-Witt and Yamazaki for building lattice models, or this high-dimensional version of lattice models where I claimed that you should have surface defects inside the 3 dimensions, this we haven't explored, but I'm very hopeful that something similar should work and the tetrahedron equation should fall out of it. But none of what I said is relevant to that story. Right? I've talked, yeah.
So you have the principal kernel model?
Yes.
And now if I did not know it was integrable, what would I do? I would start quantizing, I would write particles, but
so
where do I see this extended degrees of freedom, these infinite lines, if I look at that model? Because that's what you should scatter, right? You should scatter infinite lines.
The reason that you look at surfaces in R3 is because these are world volumes of extended line objects. So I think like point particles would scatter trivially if you had Yang-Baxter, if you could just move the lines apart from each other. So the point is, if you look at extended objects, they will scatter non-trivially off each other. You can't move them to make them not scatter.
And why are they rigid? Why are they straight?
This I don't know. I mean, I'm assuming there's some similar framing anomaly in this 5D theory, but I haven't looked at this at all. Yeah.
I'm not sure I understand how you're getting the surface operators out of the B's, because B's are two forms, but it looks like B doesn't necessarily have to be abelian.
B doesn't have to be abelian?
Well,
yeah, I mean,
how is this working?
The PCM example is the case where B is abelian, yeah.
Okay.
So then T star is 0, so you get a flat connection A.
No, but over here in this red box here, it looks like B doesn't necessarily have to be abelian.
So B abelian doesn't mean this is 0, because this is just the action of the Lie algebra G on H.
I see. Oh, so in
A
general,
is valued in
a
G, B is valued in H. This is the action of a G on H.
Okay, so B always has to be available.
So this equation stays the same if you have a billion H, which is the case where most interesting examples come from. But yeah, it's.
I mean, can you have non-abelian? I would think you don't have any idea of area ordering like that.
So I mean, I think you can still define two holonomies in these. So you can take. So this is a very technical story, but let's say you take B to be. So G, you take H to be equal to G, so the same group. So it's completely non-abelian. Then T is the identity map. And then in that case, it turns out that these two gauge transformations I talked to you about, which we ignored, they actually allow you to sort of trivially gauge away everything. There's no field content left. So to get something interesting, you have to take H to be partially abelian. And so the only case we've looked at is where H is fully abelian, and you get an interesting model out of that. But there's lots of data to play with. You can take H to be partially abelian, and I mean, there's two groups to play with, lots of maps between them that you could choose, as long as they satisfy all these conditions of a Lie2 algebra. But yeah, so this is a technical point. I'm happy to discuss it later, but yeah.
Okay, so...
Can you do higher dimension?
Yes, so the point of this story is you could technically just crank up the dimension as you wish. You just have to get more and more fields, so there'll be a 3-form field C in 6 dimensions, and you could possibly go higher. The other thing you can do is you can take Riemann surfaces. The thing about 60 holomorphic Chern-Simons is that it's crucially living on twistor space, which is R4 cross CP1, and we don't know how to do elliptic models in that case because twistor theory has crucially the CP1 factor. But in this story, there's no requirement for this to be a CP1. You could take a Riemann surface. So there's lots of sort of ways to extend this story.
Okay, so
The last question.
Thank you. Very nice talk, and very naive question. So is there an analog of RTT for lattice models in 3D, and therefore some sort of integrability equations of Bethe ansatz? What is known about that?
So so there's some papers on this, and the speculated RLL relation has 3 L's. Basically, so the tetrahedron equation has involves 4 indices 1 to 4 rather than 1 to 3, because each R matrix has 3 indices, and then so you have 4 factors of R equals another 4 factors of R. If you represent the 4th factor or the 4th index, then you get L for 3 of these R, so you get RLLL equals LLLR. This would be the analog of RLL. And there's some very interesting stuff to explore. For example, in the classical version, what would the corresponding classical RLL relation be? So a Poisson bracket of L with L equals something. So there are some speculative papers on what kind of structures should emerge in this story, but it's, I think this is sort of a playground to sort of really investigate this systematically, to produce lots of examples of these theories.
okay, so let's thank Benoit again.